Okay, so 10.8 talks about similar solids. If you remember, we talked about similar figures with area before, and so this is going to be very similar to that. And so if you remember on the similar figures, we learned that if the ratio of dimensions or sides is A over B, then the ratio of the areas is A squared over B squared. And so there's this idea that we know that two shapes are similar, and then that means they've got a similarity ratio that we called A over B. And then if we square that, that tells us what the ratio of the areas are. And the mistake often is that we try to make the ratio of the areas the same as the ratio of the solids. The easiest way to see that is in a square, right? If you got a square that is 3 by 3 and a square that is 5 by 5, the ratio of these areas is not 3 to 5. Squares are similar to each other, so they're similar shapes. And so 3 to 5 is the ratio of the sides, the similarity ratio. But the ratio of the areas is 9 to 25, which is just 3/5 squared. Well, for solids, similar solids are defined similarly to similar polygons in that they are solids that look exactly the same, have corresponding dimensions the same, but have a different size. So, for example, you might have a rectangular prism, for example. These might be your two rectangular prisms. And so there are three dimensions that we're worried about here. And so let's say this one is 4, 2, and 6. Then this one would have to be similar, would have to be something like 3, 6, and 9, where you multiplied each of the sides by 1.5. And so you can see the ratios are 2 to 3, 4 to 6, 6 to 9, all of which are 2 to 3. Well, when you get into three-dimensional, we now add a third measurement, and that is volume. So, just like before, if we have the ratio of dimensions is A to B, then the ratio of the surface area, and this is theorem 10.12, then the ratio of the surface areas, which is similar to the ratios of the areas when we're talking two-dimensional shapes. The ratio of the surface areas is A squared to B squared, and then the ratio of the volumes. Now, what this means, and this is a super important point, is A cubed to B cubed. Because of the way the math is going to play itself out when you start doing problems with this, so A cubed to B cubed, you can't just go straight from knowing the ratio of the volumes to the ratio of the surface areas. What you almost always are going to do is you're going to go from usually being given something, this should be surface areas here, something about the surface areas or the volumes, and you're going to have to take it back to the ratio of the dimensions and then square or cube it to get to the ratio of the other thing that you want. So, for example, if you're given the ratio of the surface areas of two similar solids is 4 to 9. Now, let's actually do something different. Is 9 to 16. If the volume of the smaller is, let's say, 81, what is the volume of the larger one? Okay, so if the ratio of the surface areas of two similar solids is 9/16, well, what you always want to think about is, I know that the ratio of surface areas is a squared to b squared, where a over b is my similarity ratio. So I set 9/16 equal to a squared over b squared, which is an equation I can solve for a over b by taking the square root of both sides. And so I get 3/4 equals a over b. So the ratio of the sides is a over b. Well, what I want to know something about is the volume. Well, the ratio of the volumes is a cubed over b cubed. So the way that you find out that ratio is by cubing 3/4. And so 3/4 cubes becomes 27/64. Don't try to go straight from here to here. You will make mistakes. It's very challenging to do. Always go and take this intermediate step to find out what the ratio. And so you're going to do that by, if you're given ratio of surface areas, take the square root to get the ratio of the sides. If you have the ratio of the volumes, take the cube root to get the ratio of the sides. So anyway, so we get 27/64. And so we want the actual volumes. And so the ratio of the volumes is 27/64. The volume of the smaller one is 81. And so now we go through and solve that equation. 27x equals 81 times 64. 81 times 64 is 5184. And so x just turns out to be 5184 divided by 27, or 192. And so the ratio of that volume just turns out to be 192. The other kind of problem you'll get is, you'll be given where you have the ratio of the volumes. And so you'll get the volume of the first one equals, let's say 27. The volume of the second one equals 125. And you're given the surface area of the smaller one is 63. You need to find the surface area of the larger one. Well, you're given the actual volumes of the shapes. So because of that, you can say, I know that the ratio of the volumes equals 27/125. But what that means is it equals a cubed over b cubed. That's what you have to do. So you take the cube root of both sides. The cube root of 27 is 3. The cube root of 125 is 125. That is going to equal a over b. And so if the ratio of the volumes is 127/125, you take the cube root of that to find the ratio of the sides, which is 3/5. I want to find something out about surface area, so I need to square this to say, oh, that means the ratio of the surface areas is a squared to b squared. And that gives me 9/25. Now I can solve the problem. 9/25 equals 63 over what I don't know. I cross multiply, and I get 9x equals 25 times 63, which is 1575. Divide through by 9, and x equals 175. And so 175 would be the surface area of the larger of the two shapes. If you're just given the ratio of the sides, then it's really easy. You just square or cube to find the ratio of the surface areas or the ratio of the volumes, whichever it is that you may need.